Barky the Physics dog, and I have a test on the emission spectrum tomorrow. I wish there was a convenient video someone made that could help me. Lucky for you, talking dog, I have a cringy video to teach you about the emission spectrum. What are the chances of that? And also, how'd you get in my house, boys of a human? Never mind that. Just prepare yourself for 3 cringy demonstrations to help you learn about the emission spectrum.
No, but it's like really cringy. I apologize in advance for what you're about to see. Let's just get this over with. The first demo we're doing for the emission spectrum is the flame test. To perform this test, we are going to be using pieces of metal, different element ions, and a Bunsen burner. The first ion we'll be using today is the calcium ion. Now Derek is coating the piece of metal with the calcium ion. He then inserts the metal into the blue cone of the flame. This is the hottest part of the flame. A bright orange light is emitted from this flame. This is the calcium ion burning. The next ion we are using is the lithium ion. You can instantly see the drastic change in color. This appears to be a sort of hot pink and less intense than the first one that we examined. The third ion we are testing is the barium ion. Derek again coats the metal with the ion. He then puts it in the flame. This appears to be orange also, but less intense than the first one that we examined. The last ion that we are going to be testing today is the strontium ion. When Derek puts the ion in the flame, you can see that the flame is more red than the lithium and less intense too. At the conclusion of this demonstration, you can clearly see that we get 4 completely different colors and intensities emitted from the ions. This is caused by the electrons in each of the different elements, which jumps from an excited state to a ground state. Here is the electron configuration of an element in the excited state. The second orbital only contains 1 electron, but in the ground state, you can see that the second orbital contains 2 electrons, where the third orbital only contains 2 now. So the electron jumped from a higher energy state to a lower energy state. This emitted energy. This energy can be seen in wavelength. Wavelength shows different color. That is why when we burned our different ions, it showed up as different colors and intensities. The different amounts of energy emitted from each of the different elements create different colors because of their different wavelengths. The equation to find the difference of energy emitted between the levels is Planck's constant, 6.63 times 10 to the negative third joules per second, times the frequency of photon. This can help you find the different wavelengths of each of the elements, which produces different colors in the visual spectrum. This means that our test results were successful in finding different colors and intensities within the different ions. Our next demo is with the spectroscope.
This, as many former chemistry students will recognize, is a spectroscope. It uses a prism or diffraction gratings to separate light waves based on wavelength. Both of them produce the same thing, but diffraction gratings are just more common. Now, as you already know, or should anyway, the emission spectrum contains the different wavelengths of light that a substance emits due to an energy change. The sun produces an almost complete spectrum, with relatively few gaps in between. These gaps, however, are important to identifying the elements in a star. For the sun specifically, they are known as Fraunhofer lines, named after the German physicist Joseph von Fraunhofer, who discovered them in 1814. These lines line up perfectly with the emission spectrums of the elements in the star that emits the photons. They are produced when photons released from those elements pass through the cooler outer layers of the star and are absorbed. Fraunhofer lines usually are invisible with common spectroscopes because they need to be precise enough to display them. Instead, you just see the full visible spectrum. Lens flare, commonly seen in movies, is caused when light hits a lens that has what is known as dispersive material in it. Dispersion is the separation of visible light into its different colors, so a dispersive material is anything that can cause this to happen. A light wave traveling through a transparent material interacts with the atoms of that material. When a light wave hits an atom, its energy is absorbed by that atom. Absorbed energy causes the electrons in the atom to vibrate, but if the frequency of the light wave doesn't match the frequency of the vibrating electrons, then the light will be re-emitted by the atom at the exact same frequency. Snell's law states that different wavelengths refract at different angles. The equation for this is n equals c over v, which means the index of refraction, or the angle at which the light is refracted, is equal to the speed of light in a vacuum over the speed of light through that material. The angle between the original beam and the emergent ray, or the ray of light that comes out on the other side, is the angle of deviation for that specific ray. The end results that you see are those discolored shapes on the screen.
I'm supposed to say I learned something, right? Yes, if you want a treat. I learned so much! Thank you, Strange Figure, for just happening to have a video when I needed it. It's almost like you were just trying to include a cute factor into this video. That was the video. Bye!